Hey, Hiram, you're here. Okay. Well, you know what? I don't know if we're supposed to have a class today, but we can have a class. It doesn't matter. Anybody who wants to join can join, obviously, and we can talk about anything related to our subject. Um, you know, and today being Veterans Day and all, you might have seen our president's message too, right? Um, and take a moment to recognize them, because in every country where people like us enjoy freedom of speech and thought and expression, many people don't pause to think what it would be like if they didn't have it, right? And then so you can put a price on it and say, well, how much would you be willing to pay if you could have freedom, right? Imagine that you didn't have freedom and you were in an oppressive regime, and most people would say, I'd give anything to be free, right? And and so the people on the border are the ones that get us there or give it to us. So we just recognize them today, which I think is very nice, right? So it'll just keep that in the forefront of our memory all the time, because people forget, and annual events like this will remind us that freedom is not free. Freedom is something that lots of people are paying huge amounts of their own freedom for, so that you can have yours. All right. Yeah, Madison's here, Agnes, Hiram. We have a decent class size today. We can play it by ear.
Morning.
Hey, morning, Agnes. You're back.
We're the usual suspects.
Yeah. Hey, yeah, you know what? We did talk at length about your post on the temperature coffee thing. Okay.
Apologies if it was incorrect, but it was my guess.
No. In fact, we were hugely grateful to you. You should watch the video. You didn't watch the video then. You're apologizing.
I was inundated with work the past couple days.
So yeah, if you watch the video, you wouldn't be apologizing.
I certainly will go back and
it's
check it out.
Yeah. So the whole point of that was to make you a positive example and say, it doesn't matter. It's important to take a stab, especially a quantitative stab. And it's quite unintuitive sometimes. And I was, it occurred to me during that class to mention something I learned when I was back at SRI and in the value creation workshop, and that it's important to get things into numbers, even though it doesn't make sense. Something that gives you an anchor to detach and then say, now I can look at that and continue to refine it. Does the model fit? Does the model fit is really what we're asking, right? So even in I've seen this even in machine learning experiments when we have teams. Some really brilliant people might have a good gut feeling, right? A good gut feeling, but an incorrect gut feeling. And they may spend months, a couple of months just going down that rabbit hole. Because I don't know where I was going that gut feeling. Why was I talking about that? Yeah, it's important to get things down into numbers. Okay. So so once you get the gut feeling down, then you can start saying, okay, well, you know what, this is what the model is supposed to maximize, optimize in terms of numbers. Right? We'll just bring it down to some proxy, right? And something that's measurable or as close as possible to the actual thing. And then we can say, okay, now I can detach myself, don't have to be attached to my idea so much, so that, if it suffers a few bruises, that's okay with me, because it's not me, it's the idea. And then we can basically just, chip away all the hard edges and refine it. And so I think that is what I learned was that, detaching yourself from the problem does miracles to letting you find a solution. And that's where I was going, right? So even in machine learning teams, I've seen people pick the wrong model, because it gives them a gut feeling, and they will try to refine that model. The thing is, you can always, I don't know how, so in math and stats generally, right? So you can pick any distribution and then start creating exceptions, outliers to that distribution, and you'll say, this is the model. This is the model. Everything that doesn't fit is basically an outlier. And then you can tweak parameters here and there and introduce the least kinds of, you can fix it. It's like patchwork, band-aid to a scientific theory, right? There's lots and lots of places, and then you can make it fit. And the danger there, I think, is for many people in data science is to latch on to a wrong model early on. Especially, if you are a person that is prone to coming up with lots and lots of really good work and good ideas, it's important to detach yourself from the idea. Because if you get too wedded to a wrong idea, then you can spend a lot of your mental cycles just, trying to patch it up with Band-Aid, instead of saying, well, you know what, there's too much Band-Aid here. I should probably just, do this Kuhnian revolution kind of thing and pick a completely new paradigm altogether. Right, and often that works, right? So and you may say, well, this is gradient descent is not the right way to tune this because there's too many local minima, right? So we want to find some other way of finding the optimal result, and things like that. And people don't even think about that because when you're in the minima, everything around you looks like it's going down, and so we're optimizing. No matter what you do, you're getting an improvement, and so that's the kind of rabbit hole that I think. Is good to that's what it helps this practice helps us not go into. I think that's coming back to the this practice of quantifying things and objectifying it helps us not go down the wrong rabbit holes for the wrong reasons, just because we invested too much effort in it, or we like it, or society says it's the right thing to do, or whatever it is. You're attached to it for if you feel too special about being attached to it, you're not going to look at alternative approaches. And that's why sometimes it helps to have a manager. Even in every machine learning team, it helps to have a manager who can be sufficiently detached, who can afford to be sufficiently detached from the problem, so that they can always have a higher level perspective, and they may be more aware of local minima and say, okay, well, everything looks promising, but that's not what we're shooting for. Let's try another model. Let's try this. And and so the quantifying things. So Agnes was very helpful, and in fact, Agnes was the only person who posted, if I remember correctly. So thank you so much, Agnes.
Anytime.
And you should see that video, because we actually did develop the thought more in class, and tied it down to black body radiation and things like that. Hiram helped with playing with the Desmos, and it was really cool. I think it was cool. Maybe you should bookmark it and check it out. Well, today.
Yes.
Yeah, sure. Go ahead.
Saw that you did linear and binary search.
Yeah, we could do
for the
that.
code.
Yeah. I think that's the one.
Very cool.
Did you guys complete it last class? I'm sorry, I didn't watch the end of that video.
No, we were working on binary search.
You should work on it on your by yourself. Okay, I'm not going to walk you through binary search.
Okay, no, we did not finish it. We pretty much finished it, but you said maybe.
Good. All right. So then you can start working on the rest of that thing. You have 4 to-do items, right? To time them. Yeah, so I think that'll be exciting. That'll really be exciting, because once you time them, this will be a good lecture to do that. Once you time them, you have to sort it for binary search, and we need to cover sorting techniques. We could do a bubble sort, insertion sort, something like that. No, I think what you should do is just read up. We're not doing sophisticated sorts yet. We're just doing these n-squared sorts mostly, right? So read up on this. Is this in the exam? Maybe there's going to be questions in the exam, okay? Which touch upon, but not too many points. There'll be at least 1 or 2 points, I think, which touch upon sorting techniques and your intuition behind sorting, but not the sophisticated sorts. Just do the insertion sort. I think bubble sort. Bubble sort is very easy, right? I can describe it to you in 2 seconds, right? All you're doing is finding the minimum and yanking it to the top, then finding the next minimum and yanking it to the next position, and keeping and doing that, right? And you're yanking it, meaning you find the minimum and swap it, right? Just find the next minimum and swap it, and keep doing that n times you're done, right? That's bubble sort. That's everything is sorted. Yes or no? Yeah. So, but to find the minimum, you're going to have to examine n items first. Yes or no? Everybody has to say yes or no. Okay. So to find the minimum in n items, how many items are you going to have to look at?
-1.
No, you have to look at n items to find the minimum of n items, right? But n minus 1 is okay, good. It's good enough, right? But you're going to have to look at n items to find the minimum of n items. Yes? Okay, good. Now you found it. But to sort the entire thing, you still have to find another minimum. Yes or no? Okay, and that minimum belongs to how many elements? The next n minus 1, yes, because you've taken the least one and stuck it in index 0, and then what's left is everything else. So only n minus 1 elements. So you got to find the minimum in the n minus 1 set and yank that to the top of the n minus 1 set. And then you're left with n minus 2. Yes? So if you keep doing it all the way, so you get 1, 1, 2, 3, 4, 5, 6, n. So how many times have you looked at all these items? The first time is n times, yeah, n plus n minus 1 plus n minus 2 plus n minus 3 and all the way up to 1. Yes? Okay, so addition is commutative, so you can basically say it's 1 plus 2 plus 3 plus so on up to n. Yeah, and what's the sum of the first 10 natural numbers? Right, arithmetic progression, right? So the sum of the first n natural numbers, it's right, it's n times n plus 1 over 2. Yeah, so the first n natural numbers is n times n plus 1 over 2. If you sum them all together, you can check it out, right? You can prove it by a million ways, and with mathematical induction or the Gaussian way. Actually, there's a bunch of lectures recorded on this topic when I think maybe in class we probably took an entire 15 minutes to just marvel at that proof and how it can be done with mathematical induction and derivation, and they're all the same thing. So I think if it'll be nice if someone can locate that video and watch it. But anyway, so where we're going with that is to sort it, it's going to take time that is proportional to n squared, because n times n plus 1 over 2, n squared plus n over 2. Yes or no? So to sort n items using that very primitive. No, I shouldn't say primitive because it's not primitive, right? It's not even trivial, but it's just an inefficient way. The bubble sort is an inefficient sort, right? So sorting in that inefficient way, it's going to take n squared examinations on average to sort it completely. Yes? So that's why we say sorting is actually, no, that's not why we say sorting is inherently an n squared problem, quadratic problem. The reason we say that is because intuitively there's n squared pairs. N choose 2 pairs, right? N times n minus 1 over 2. So if you were to rectify every inversion, because if the list is not sorted, if there's one pair of it, if you can identify at least one counterexample, saying, hey, this list is not sorted because these 2 items, they're supposed to be like that, but they're like this. So just one pair. You just said one pair out of there in that list is out of order. So that list is not sorted. Yes or no? Okay, so how many such pairs are there? There's n squared such pairs, right? It's n times n minus 1 over 2. So if you were to do it by brute force, right? Some brain dead brute force method to sort a list, it's going to take n squared of the order of n squared comparisons, because it's n squared pairs you need to check, and every pair that's inverted you're going to put back, right? Once you've rectified all of your inversions, everything that's inverted you're going to rectify. So once you've rectified all of your inversions, your list is sorted. Yes or no? Yeah, okay. So we say that the brute force sorting algorithm is actually n squared. It's going to take you n squared examinations to rectify that list completely. Right? And so now this is where the juice of computer science really starts to come in, because now you're saying, okay, now that is the brute force way. Are there ways in which we can make it better than n squared? Right? And there's so many different ways, and each one is maybe a stroke of genius here, some clever technique, So if you look at each sorting technique and say, well, I just need to master these techniques. Yeah, okay. You just put in a lot of effort trying to do that, but don't try and master all of these techniques right now. Just pick a few and try and get an intuition of what they're trying to do, and also try to get an intuition of what they're trying to do wrong. Right, so bubble sort. Think about bubble sort, right? Hey, okay, it sorts it, but if I was bubble sort, I wouldn't be doing it that way. That's the way you should be thinking, right? So you can look at all these n-squared sort methods and say, well, what are they doing wrong? All right, what can I do to improve them? Because there are tons of improvements out there, I can tell you. So if you look, you can look it up. You can just go on Google and say better sorting techniques. You're going to come up with a whole bunch of ones, right? So don't look at any of them. Just look at the inefficient sorts. Start with the insertion sort. Insertion sort does have a lot of scope for improvement. In fact, insertion sort in 2A is what's going to turn into shell sort in 2B, right? Because an insertion sort really is an n-squared sort, because we're just comparing adjacent items like that. Bam, 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 bam. So adjacent items and flipping them and so on and so forth, right? And it's a real pain, because sometimes this item has to go here. Why do I need to bubble up slowly, like bam, 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 bam? If this needs to go there, why don't I just swap it directly with that? So I can save like a whole bunch of swaps. Yes? Okay, so that is the intuition. Oh, I shouldn't, honestly, I shouldn't, you just forget I said that. Okay, these are things that you should discover yourself, because this is the juice of sorting, right? So look at bubble sort and see how can I improve it? What can I do? What are they doing that's useless, right? And how can I get rid of all the useless stuff? And and then you can bring a lot of the cleverness. And then in 2B, we can study shell sort, which is really an improvement over insertion sort, using exactly the intuitions that you probably have got when you're looking at these things. And then later on in 2C, we'll just look at so many more different sorting techniques, even different sorting paradigms, right? Different sorting paradigms, and say there's so much ingenuity that has gone into the subject over the centuries, really, right? But we have a record of this, at least in the last several decades. And
is a sorting paradigm different from a sorting algorithm, or are they?
Yeah, you can actually use different sorting paradigms altogether, right? Because you can have a comparison sort. A comparison sort is basically where you're going to compare two items and rectify these things.
Right, yes.
I don't want a comparison sort. I want a pigeonhole sort, bucket sort or something like that, right? You're going to take an item and just stick it into the right index, or a hashing sort. You can come up with different, right, which don't require comparisons. And sometimes you can come up with domain-dependent sorting algorithms, which exploit very critical facts about the domain that general sorting algorithms don't know.
Did it not freeze for anyone else?
Yeah,
oh, sorry. No, my internet's terrible. So you just froze and I lost your audio.
Is my audio cutting out for you guys?
Right now it's fine.
Oh, I'm sorry. I just got a flashing message that says my internet connection is unstable. Why the hell is my internet connection unstable? Wait a second.
You gotta get that gigabit or something like this.
No, it is connected to my router. All right. Hey, Google, can you check my internet speed?
Okay, testing the internet speed. I'll tell you the results shortly.
Okay. All right. Anyway, so I don't know. I'm supposed to, I'm sitting right next to that's the Wi-Fi router right there. Can you see it? Well, you can't. Well, anyway, there you go. You see that light over there? And that's the router, and my Mac is right here. So I'm surprised. And I don't have a lot of load, right? Elsewhere here. Can you all hear me now? Hopefully, hopefully some of this audio makes it into, at least into the YouTube video.
Your network speed test has finished.
Yes, they're good.
Currently 57 megabits per second, and the upload speed is 6 megabits per second.
That's more than enough for Zoom. All right. All right. So anyway, as long as if you can't hear me, just make some visual gestures. Okay, just say something like this. Okay, I'm bound to notice that. Yeah, sorting. I hope I don't know what I said, so I can't repeat what I said about sorting, but it should be in the video, right? It should be in the video, and hopefully that is not cut. Audio problems. No, if the audio got cut going to Zoom from here, unless Zoom received the audio late and they couldn't stream it, but they could patch it into the recording. That's possible, right? Yeah. Yes, I suppose. We'll see when we see the downloaded video. Oh no, I think I'll get the entire audio. That's fantastic. Okay, so so Zoom has two options. You can say record the video, YouTube, record the video in the cloud or record on the local computer. Okay, so and there's a checkbox. And I said, record on the local computer. So the MP4 file is recorded here. So it's probably using some client-side program on my Mac, and it's going to capture the audio. Cool. All right. And fortunately, I didn't select record on the cloud. So then, you know, we're bound by the hardware. Okay. So if you guys have any questions, we can talk about that. Today is really a freebie lecture for us, really, I think. I don't know if other, do you have other classes today? No? So today is really a holiday for Foothill? I haven't looked up. I haven't looked it up. I thought it was a special day, not a holiday. Right? Well,
I still have work.
Oh, you got to work? Okay. All right. No, but
I still have work if that makes anybody feel better.
No. But work is different, Agnes, because you know. I know when I was out there too. We just had an observance, but not.
Anand, you should take a holiday, right? I mean, isn't a university holiday for teachers also?
I'm pretty sure Foothill has a holiday today. But still, I think, you know, classes are voluntary, you know, because students and professors can just get together and on a Zoom session saying, well, you know, on a Sunday, we're going to just meet and go over some stuff. We can treat it like that. Yeah. Because the important thing is not to enjoy the holiday, right? So the idea really is not to enjoy this day, but to use that as a marker to say that, you know, we're enjoying so many things that are just invisible to us. And if it's invisible, we don't get to enjoy it really, right? We just take it for granted. It's just out there. We don't care, right? But freedom should not be invisible, right? We are paying for it. And we should, so the purpose of the day is not to just take off and bury yourself in a Netflix video so that we wake up next day, you know, after a party saying, okay, that was a holiday gone. But really to think about, you know, what people are sacrificing to, so that we can enjoy what we're enjoying and what we're willing to give up for that, which I think we had an opportunity to reflect on this class, I think. Yeah. Yeah, so you can ask me anything really, given that this is a freebie lecture. And, you know, but I'm really concerned that we're losing 2 days, right? That's one whole week is gone, right? Because Thanksgiving is on Thursday. That's one lecture gone. And this Thursday gone. That's another lecture gone. Okay. And then week 12, we're not supposed to introduce new material. Right. So that's 4 lectures gone. That's 2 weeks gone out of 12 weeks. That's 10 weeks. And I don't think it is fair on students to inflict that material, you know, all of the material we have lined up in 2A in 10 weeks and expect you to learn that. So that's why I think that, you know, these shouldn't really be holidays, but, you know, special days. So we should still use that to better ourselves, right? And make use. This is the way that we should put the freedom that has been hard earned for us to good use, right? Not to put it into a Netflix show, right? So someone has worked so hard to give us the opportunity to do this. Let's actually say, let's make something worthwhile out of it. Let's try and learn something new. I think that's a great attitude. So yeah, any question you have, I'm happy to answer. You know, we talked about sorting. It wasn't on plan to talk about sorting, but we did talk about sorting. If you want, you can start working on your code right now. I can step away and like last class, right? You can cut the code, finish up the binary sort, and then start experimenting with different size vectors, and then do the timing, right? So we take the same thing that Alexandria did last time. Someone did last time, right? I forget. Who?
Oh, it was Hiram.
Hiram.
Yeah.
Take the same code. You know, you can just copy and paste.
Wait. What? I don't remember doing the timing.
No, we did binary sort.
Oh yeah, I wrote it.
But you wrote it. Yeah.
No, I'm not talking about the timing code from last class. I'm talking about the timing code that you wrote even before that.
Yeah.
Oh,
That's
yeah.
Copy by rough. All by copy and rough. Didn't we time that?
I did.
Yeah, we timed that. Yeah.
Yeah. If you have a link to that code, just copy the code that does the timing and just borrow the same thing. Okay. That's how most of the software engineering. And you see what happens. Okay. Just take that and time your methods. And if you have time today, I would really, really love it. You know, honestly, we haven't even started today. We haven't even got to the time where we usually start class. You know, I have a feeling we've talked about a lot of stuff, trying to keep the airwaves occupied, and it's not even 8:30 yet, right? Which is usually the time when we start class officially. So that's great. So we have a lot of time, and I would really love it if we could today manage to run the timing experiment for linear search and binary search. For vectors, should we time vectors? Yeah, I think we should time vector sizes, right? So we choose a vector of 100 items, and then 100 all the way up to 100,000, right? 100 all the way up to 100,000 vectors with random integers in them. Use the same random integers for both, both these guys, okay? Exactly the same vectors. And inside, you're going to generate, you're going to find, I don't know, 1,000, each one of them, you can do 1,000 searches, right? 1,000 random numbers, and search for the same 1,000 random numbers, same vectors, okay? Try and control everything as much as possible, and get the timing, and we'll try and plot it, right? So this time, let's get it all in the Google Sheet, and then we'll highlight the columns and say, create a graph from it, and we'll look at the shape of the graph and things like that. And then we'll also go to Desmos on a different tab and plot the two graphs and see how the things match up. I think it'd be very fun. I think it's going to be a fun exercise. All right. Can I just I'm not going to go away, right? I'm just going to be here. Right, I'm just going to be here doing stuff, and I'm going to be listening to what you guys are saying. So just call out to me if needed. Is that okay? Great.
Yeah.
All right, Hiram, is that okay? Agnes?
Yeah, it's fine. I just had a quick question.
Yeah, sure. Before I go, I'm happy to answer any questions anyone could have. And if you happen to have a question when I'm not here, just call me back, okay? And say, hey, I have a question, and I'll come back, okay? Because I'm just listening all the time. Okay. Oh, okay, good. Sure.
So we never actually talked about constructors and destructors, and I've used constructors before, but I'm not exactly sure how to use a destructor. Okay.
All right. Good. Strangely enough, I'm glad you brought the question up, because if you look at I'm going to talk about destructors. Okay. I'm going to tell you what the destructors are. Okay. However, this is my recollection. The reason why destructors are not formally covered in the syllabus or something else is historical, is because destructors were not part of I think, right? You should probably check it out. You can do a Google search or something like course ID, State of California, CS2A or something like that. And it says, we should talk about constructors, but not destructors, or something like that. And why is that? Why is destructors not included in CS2A? Because we do talk about pointers at the end. Yeah, at the end, not now, because until we start allocating memory. So here's the thing. Okay, let me talk about the constructor. A constructor is basically a method with the same name as the class. This is a special name. That's how the compiler knows it's a constructor. Okay, a constructor is a method that is invoked every time the compiler needs to make an object of the kind you ask for. Right. So let's say you have a class called animal, and you create a new animal. Say animal, my animal. Yes? In your code, you have animal, my animal. Okay. Now, when you say int, my int, the compiler knows. Okay, well, I know all about ints. It's 4 bytes, and it's it'll stick 4 bytes in memory and tag it with Hiram asked for this. Okay, these 4 bytes are Hiram's XYZ. Okay, so it could do that. However, you said give me an animal, my animal. Okay, he doesn't know, the compiler doesn't know, right, what animal is. So however, you told it. Okay, all right, don't worry, dear compiler, right? I'm telling you, this is my animal class, and someone asked for the animal class. This is what you're going to make, right? You can also go one step further and say, when you need to make one, this is the code you need to use, all right, to make that object. Okay, now you don't have to give the code to that compiler, because compilers are clever enough to write that code for you most of the time, right? Most of the time. That's why we don't write constructors in the early stages for CS2A, because we're just using simple objects. A simple object is basically an object that has a lot of primitives packed into it, right? If you have something like that, the compiler basically just looks at it like a structure. And so, you want a new one of those, I just make one of them. So I just need to get all these guys together and put them in, in the line that you asked for, right? So it can make it, so we get freebie constructors all the time. In 2A, we can use freebie constructors all the way up to week 11. Maybe that is the reason why it's left out, okay? Or maybe pointers were added later on into the syllabus, okay? Memory allocation and so on, and that was a typo. They missed saying, oh, now we can do pointers, but we haven't done destructors, okay? So maybe we should fix that in the CID, okay? So that's a good point, thank you. I'll take that back to a department meeting. These kinds of things, simple things like this, getting it, filtering it back and ironing these creases out of, it's a multi-year process, right? Many people think, it's just a bunch of people sitting together in a room, consortium, coming up with this. No, it's a consortium gets together and puts together what they think is workable. But then we collect feedback and like this from students, from staff, from faculty at many institutions. And we have these meetings where these things are refined over many, many years. Okay, so like this, maybe this will filter into the system at some point. Okay, so yeah. So when you have simple things like that, we can deal with the compiler doing both the constructor and destructor, and in many cases we're better off telling the compiler to do both, right? A destructor is also like that, right? When you don't need my animal anymore, it is using up resources. Yes, when you don't need an integer anymore, right? You have let's say you have a block, right? A bunch of statements. Okay, so let's say you have a bunch of statements in main. Okay, and you have an integer here. Okay, or function, some function, you declare an integer here. Okay, that's the end of the function. Okay, after that function ended, that integer is not needed anymore. Yes or no? So the 4 bytes occupied by that integer need to be freed up for someone else to take. Okay, just like that, you create an object here, animal, right? At the end of the function, my animal is gone. So, but there's a whole bunch of bytes in there, not just the 4 bytes for the integer. Maybe you got a name and all these things, right? So all of those guys need to be freed up one by one, bam, 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 all right. So if they're all just primitive objects, the compiler needs to knows how to do that also for you. However, because these languages give you the ability to make the constructors as complex and sophisticated as you want, right? They don't just have to be packing stuff together. Constructors can be doing a whole lot of sophisticated logic, right? They could be putting stuff together, computing things, many things, right? If you do that, and sometimes one of these constructor guys might say, give me a new resource, give me a hard disk somewhere, right? Or give me memory, allocating resources. Now, if you have a constructor like that, you cannot rely on the compiler to destroy it for you, because it'll just, it's not going to know all the complex logic you've done inside of the compiler, right? Inside your compiler, you call some function, and that function went and allocated a big ass chunk of memory, right? So how does the compiler know? So it'll just say, free up all these local guys, and that is called a memory leak, right? So until the time when you start allocating resources inside of your compiler, or doing some, crazy things, like not crazy things, doing some, it seems messy, but sometimes it's necessary. Okay, suppose you want to maintain a population variable. Again, this is something like a static, right? A static, and in fact, you can't do this in Java, right? It's really hard to do something like this in Java, right? And so, someone who's doing Java, you can tell me how you can do this. Okay.
I was gonna ask, and hang on. So is this about? So this is mainly about memory management, right? And
no, it's not even about memory management. I'm talking about
it's not like the garbage collection.
No.
It's not.
Java has something where the garbage collector will run it. Like you can write a destructor, but it's really bad, and it's really unreliable as to when the garbage collector will come get it. So
but I'm not even talking about that. We're not even going down the memory route here. There's something very simple. Very simple. I'm going to explain something very simple that you can do in C++, but you cannot do you cannot do easily in Java. Okay, you can do it in Java, but you cannot do it easily in Java. Okay, yeah. If you can find out, those of you who are Java programmers, you're welcome to share this in the forum, saying, "Hey, you can do this in C++. You can't do it in Java, but we found a way to do it." Okay, that'll be really cool. Suppose you have your my animal class or your animal class. Okay, inside of the animal class, you have what is called a static variable. Okay. A static variable is a variable. We didn't talk about this in class, but I promise that we'll just touch upon it in a different discussion. Okay, so I told you, right? We'll have an opportunity to do this, and this is that opportunity, I think, right? So a static variable is basically a variable that's part of your class. However, that variable is not attached to every object that you print out from the class. Each object does not have its own copy of the variable. There's one copy of the variable, and it lives on the blueprint of the class. So every object, every millions and millions of objects out there, when they change that variable that they think is contained in the object, secretly, that variable is actually tied to that singular variable that lives on the blueprint. Every guy can change that one guy. That is called a static variable. It's basically you have a house plan, okay, and you write something on the blueprint versus writing it on the wall of every single house, right? Because once you build a house, each house is modifiable on its own, right? But all of the houses are based on the blueprint. Now assume that every house had a direct line to the blueprint, right? And they could go in and do stuff to the blueprint, right? Obviously, they can't go and modify other houses, but they can change the blueprint so that anyone who looks at the blueprint is going to change, look at the changed one. Yes? So there's only one class, one template, one class template, many objects that come from it. Now, each object has a bunch of properties. But you could also make the class template have a property, which can be changed by any object. Isn't that cool? That means inside of now, even in Java, you can have static variables. I'm not saying you cannot have static variables, okay? You can have static variables. Now, assume that in my animal class, I have a static variable called population, okay? And every time the constructor for animal is called, okay, that constructor code of that object is just going to increment population. So at any time, I can basically look at the static variable and say how many animals I have out there in the world. Yes or no? In fact, not only me, any animal can look at its own population variable, which is basically a global inside of the class, right? Any animal can look at its own population variable. It'll tell it directly, right? Real time, how many animals are out there, right? It's like one of those counters on web pages, right in front of your eyes. Every animal can look at that counter and just bam, 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 increasing as more and more people are forking off animals. Yes?
Is the main use for it really as a counter, or is there another use
I'm just saying it's a
for
static.
these?
It could be anything.
Right.
You can have many static.
Of course.
Yeah, you can have many static variables, right? So I'm just using population as an example, right? And let's think of other static variables, right? So by the end of class, or someone could share on Reddit forums. It's like there's so many things that intuitively we think that shouldn't be part of objects. It should be part of the for example, blueprint. On a blueprint, you could have a static variable that says number of walls. Okay, and it's up to each individual house to say where to place the walls, but the total number of walls is fixed, right? And that's on the blueprint. And if you want a different number of walls, you change that variable. It's pretty much like a different blueprint. There's things like that, right? And that sounds very contrived, but I'm pretty sure we can come up with use cases for static variable. It's very useful, right? So, but that's even not where I'm going with this. I'm saying now, suppose this population thing is only useful to me if none of the animals, if every animal created is an immortal animal. If I create an animal inside of a function, right, and that function never ends, then the population is not going to decrease. But what if that function ends? That animal that was created is now got to be destroyed. Yes? Gone. So the population has come down by one. Otherwise, the population is always in an increasing curve. Yes? So now C++ gives you a hook, right, to your destructor that says every constructor can be paired with a destructor, where you can do crazy things. Well, no, not crazy. I keep saying crazy things, right? But it's really messy because in your constructor, I really prefer to keep my constructors so thin and that I don't have to rely on destructors because I don't know. Sometimes you can't, right? But yeah, in your constructor, if you allocated resources and things like that, you got to make sure that you have a destructor that can handle it on the way out. Otherwise, you're going to have a resource leak. Right? So, and that is many times that's how, even not just constructors, destructors, even inside of your class, you may have a method that allocates. You should have a method that also deallocates, right? Or some way in which this goes away, because otherwise it's, you have memory leaks. So that is the reason why C++ has these constructor and destructor pairs. Most of the time, we don't care about that because the compiler gives them freebies for us, right? But if you're doing non-trivial things like allocating resources in your constructor, you got to make double sure that you also have a destructor that deallocates these resources. Otherwise, they're just going to be floating around, no owner, right?
So I have a question. Like, what kind of resources do you have to pay attention to? Like arrays?
Most of the time, no. I mean, I'm just talking about raw resources here. Raw resources like memory, magnetic media, or maybe you just tie up a whole bunch of machines, right? So you can have a function that basically just map reduces to a cloud or something like that. So each of these is a resource, right? You can talk about resources at various levels. But I think we're just talking about raw stuff like memory, disk, anything that costs money. Anything that costs money, if we tie it up, then it's bad. Okay, it should either be used by us or it should be used by someone else, right? That's yeah, that's why I even feel about money now, right? So yeah, either I use it or someone else will use it, right? So no use putting it in a vault in Antarctica. All right, so yeah, so that's why constructors and destructors are so important. It does that answer your question, Hiram? All right. So, but I'd be very interested. I'd be very interested to see posts by you guys in the forums. By the way, this extra credit stuff and stuff like that, you won't see it reflected in Canvas and things like that. But I know who is contributing, right? And thinking about interesting things and talking. So don't be worried or stressed out that you're not getting points for these things, right? So I can. And in fact, even before the final, you can reach out to me, right? As long as you're interested in class and interested in these things, you can reach out to me and say, hey, how am I doing? What am I likely to get? Is there anything I can do to, even though a grade is not important to me, I'd like to get a good grade. All that is okay with me, okay? So you can just reach out to me, right? The only people that I'm a little hesitant to cut slack to are the ones that didn't even put any effort into the class. Not because I feel that they don't deserve it, but because I feel that if I give them the credit for what they didn't do, it's basically just taking away a whole chunk of what they could have experienced, right? They're never going to do this again, right? They're never going to do this, right? If you say you pass CS2A, you're going to try and CS2B, and maybe you'll even complain in CS2B saying, I got an A in CS2A, but I'm failing in CS2B, right? So, but still, it's not a good experience for you. So that's the reason I don't cut any slack for people who don't put in effort. But I know every single one of you. Not even now, right? I know even if Robert. By the way, that person I think his name was Robert, not Brendan. I think I said Brendan. It was Robert. I know. So even going back several years, I know most of these students by name, right? Like Agnes too. I remember, even though she was an online student, I never saw you in face-to-face class, but I did remember when you enrolled in CS2B. In fact, once upon a time, I set up a system to basically just get the names of students and put it in a flat file somewhere. I'm sure it's going, right? But I never even had a need to look at that file to see, if someone reaches out to me from later and say, hey, I did your class that time. I don't need to look at that file anymore to say, oh, that was that person, right? I actually remember most of these things, so you don't have to worry. So don't feel stressed out, right? And if you are stressed out, you should just reach out to me, right? And then the guys who are, not very invested in CS2A, don't reach out to me anyway, all right? So, and I don't think that's good. So you should just reach out to me, and I will basically just cut you slack. If you're interested in the stuff, you should be cut every slack that that will benefit you. So I'm happy to. Does it answer all your questions? I'm happy to basically step away, and you can take over. Okay, you got the code and everything. You guys can coordinate amongst yourself to get the code. And all right, good. I'm just going to be around. Just call out to me if necessary. All right. And do you want me to come back at I don't know? I'll check in 9:15, half an hour from now, and then again I'll check in another half an hour from then. Right? Or you can call out to me anytime too. I'm just going to be around here. I just need to look at something for. I just need to send an email to Beta, so maybe I'll type that up now. So I'll talk to you guys soon. Okay. All right. Bye.
So if I've quoted a few times, and Hiram has too, but I can take it if no one else wants to.
Yeah, if no one else wants to.
If you fixed it and you were gonna code it, that would be great.
Okay, I did. I have it open and I fixed the binary search, and I can show you guys what I did.
That would be great.
Yeah, there were same problems I came across when doing my homework because I was testing it this morning.
Which one? 7? Is it?
Yeah, 7 starts with searches.
Right.
Was it 7?
Yeah.
Yeah, I did it like a week ago, so it was really fresh in my mind. Okay, here's what I did. And Agnes, have you seen the code yet?
I glanced at it. I really need to play some catch up. But so what exactly is it that we're trying to do here?
Oh, sure. So what we did is we're making another like big random array, right? And
yeah,
then
but
what
this-
we're gonna do is we're
I mean, I
going
guess
to-
as a whole.
Oh yeah, we're gonna like compare timing between linear search and binary search.
Cool. Okay. Gotcha.
Like a really big one.
Hmm.
Okay, so
Is
here's what
Kevin the
I
one
changed.
with, or
What?
is Kevin the one with the pet store?
The pet
Because
store.
that's the one with insertion and binary search.
Yeah, that would be 7.
Yeah.
Oh, gotcha. Okay, so one of the bugs was this was size t, and if the vector is empty, it would wrap around.
Oh, I see.
Yeah, I hate that. I've had that problem so many times. So I changed it to int. And then
Okay.
I just ended up doing what I did in my homework. So we have the +1 here, right, Hiram? Which is to like find out where there's something like this, right?
Yeah, I
Yeah.
can see. Yeah, usually you don't want to use the not equals to like break out of a while. It's too specific.
Yeah, I got
So-
into some infinite loops. I don't remember when, but basically what we were trying to do is figure out if there's a gap, and this will figure out if there's a gap.
Gap between.
Beginning I and end I, like,
Why
Mhm.
do we want it to be equal to end I as an option?
this will be 0. I don't remember. I don't know. Can you guys convince yourselves that this works?
I guess I just think that we want beginning I to be less than end I, right? Because if they're equal, then we're done with our search, pretty much.
We cannot compare, right?
Well, if beginning I and end I are equal, then we still have one item if we're looking at it inclusively. We can change it.
It's
and
okay.
just change it back if there's a problem.
Let me see. Midpoint.
Otherwise, I kept
Oh,
all
why
these the
why
same.
the midpoint -1?
Yes, so that I know this definitely works. It's because we're looking at vec midpoint, so we never have to look at vec midpoint again. So
Oh, I see.
yeah,
I see. It's because you're doing it inclusively. I see. So then you do want that equals, huh?
oh okay. So
Sorry, I was
Yeah.
assuming that it wasn't being inclusive for some reason.
yeah, so the interval's inclusive in this,
I see.
and yeah, and I tested it a few times and it looks like it works. So we can just move ahead with the timings instead of getting caught up on debugging.
Sounds great. Let's do that.
Okay, cool. You guys guide me with this, and I'll get rid of our test stuff.
Yeah, okay, so now we need to actually do all this, huh? So we have our random numbers, and we need to time them, right? So don't we need the time.h or something? Or were we gonna use
Oh,
clock
I
this
found
time?
it. We did this. I did do this. I forgot I did this. Oh, okay. You said we should copy paste. Time is in standard.
Oh, that's nice.
Yeah,
Okay.
that's good. Okay, I'll just copy this and we can change it.
Okay, so start timer. Okay, that's good. And then we just need, oh, we don't need the whole, do we need the 4 thing? No, we probably do, huh?
Which working?
Yeah, num times 1000, that sounds good. And then we need to just change that to, what is it? Time per call, time per linear search. Yeah, that's good.
Okay.
Time per linear search. And
I
it's
don't
going to be
wanna-
find index of v1, huh?
And it's called randoms. And what else were we putting in? Like a number? Target?
Yeah, we need a target number. Maybe we could look for, what is it between? Maximum
Oh.
random is 1 million. No, yeah, that's 1 million. So,
What do you guys think?
what do you think we should look for?
Where's the array of that we're searching in?
Where's the array? Oh, we're searching randoms.
Okay.
Now that yeah, and we set up randoms here. Right, yeah, we need srand.
He said to.
What was SRAM used for?
Wait, does Big Rand have an srand in it or not?
Oh,
I
good
forgot.
question. No.
No, okay, so then yeah, we should definitely set up an srand before we use Big Rand.
Okay. Was that all we have to do?
Yeah, that's it.
Okay, cool.
And then after that, we probably want to reset it
Reset.
before we use Rand again. I don't know if we're using it right now, but we have to remember to reset it. Because we want to use the same set of numbers, right?
Oh, yeah. Oh, and we're sorting. Okay.
We could make a copy of
What value
randoms.
should I?
We could just make a copy of randoms somehow before we sort it. But I feel like that's a bit.
I don't know if we have to. Is it okay if we just, let me make notes to sort it.
Because you see, the problem is if we want to sort it many times, then it's going to be sorted after.
We
after
don't
the
want to
first
sort it many times.
Okay, so then we need to get rid of the for loop when that behind the find index of v1.
Oh, well, this doesn't sort it, so it should be fine, right?
Oh, I'm sorry. Yeah, it's just looking. I'm sorry. I thought.
Yeah,
we were
you're
sorting.
thinking of sorting.
Yeah. Okay, so we're just searching. Hyperlinear search. Okay.
Okay, cool. So we'll just sort it once and then loop and do binary. And that's all we have to do. Oh, it's angry. Why is it angry? There's no time.
Oh, there is no start timer. We need our start and
Oh.
end timer variables.
Oh, and we had a big for loop, which was increasing the vector size. I see what you're saying, Hiram. So, okay, my bad. Well, we can start with this and then put it in a big for loop. Oh my God, that's terrible. Okay, well, Hiram, what do you remember how to do sort?
So what you do, you're gonna need 2 for loops.
For sorting? Oh, isn't there a built-in we can use?
Oh, maybe there is. I don't know. Maybe you can search it up. Or I would guess it's just the name of the vector dot sort.
Oh.
Or I don't know. You should look it up.
I don't think so. I looked in the vector class and there's no sort.
Oh.
But
Yeah, just try that and see if there's an error.
Okay, let's see. Oh, I'm this or not this. Okay. It does not like it. Okay. that shouldn't help, but no. Okay, let's see. We have to include something?
I don't know.
Oh. Yeah, it says include this.
Yeah, yeah, for STD sort.
Oh, so we can just include whatever we want.
We can do what?
No, no, never mind.
Oh,
The
sorry.
algorithm?
So yeah, the problem with that is that I looked into it and it wants like an iterator.
Oh no.
An
So like you
iterator?
need to say randoms dot begin and randoms dot end.
Oh. Okay.
Randoms dot begin and it's a function, so and then randoms dot end. I
Like-
think that should work.
A comma or a minus?
Yeah, yeah, a comma, a comma.
Okay.
I think that's how you're supposed to call it.
Hey, thanks.
Yay. Okay.
Okay, cool. All right. Time for binary search.
And then V2. Then
Oh, that
it's
was
the end,
easy.
right? Yeah.
Value defined. This feels
Oh, that's a good,
ridiculous.
that's,
There's so many constants.
well, I mean, better than hard coding everything out.
True. Okay, and then we can put it all in a big
For loop, right?
loop. Well, that's helpful. Let's increase num times. Oh, that won't help. Increasing num times won't help.
No, it probably will.
It slightly did. Okay, time for the for loop. Let's see. So we did like max deck size.
Oh, shoot. Wait, did you make? Okay, never mind.
All good. And then we'll have to seed inside, you said?
The seed, yeah, we're gonna, so I think what we're gonna do, right, is we have randoms. Maybe we should make it inside the for loop, but, so we're gonna
So
have
here.
randoms, right? And then with randoms, we're gonna then fill it with lots of random numbers based on the seed. Wait, what? Oh yeah, delete that bracket though.
Delete which thing?
The bracket after that for loop, because don't we want to do it lots of
let me
times?
put it way
So just
below.
delete that and then yeah, all the way out there. Yeah.
Man, I wish it had automatic indenting.
Yeah, it would be nice, but
Cool. Okay, seed should go up here, I'm guessing.
yeah, it
Well,
can.
seed.
Oh yeah, we definitely need it to be in there. Oops, I almost forgot.
And then
Yeah, and then we
this-
fill it, and then that should work, I think.
this is max. Is this n?
N, is it? Okay.
Is
Yeah, we
this
can do that.
size?
Oh, did you use num times anywhere else? Wait, no, not num times. Did you? No. Wait. Sorry, I'm just
What is it?
getting confused. I think it's fine.
I think the code is really messy right now.
Yeah.
It'll look better. Okay, so what we did in this was we didn't fill it, so I guess we fill it.
No, didn't we fill it? Isn't that right there?
To the end this time. Does this look good?
I mean, probably what we should do is I is less than randoms.size, but
Always less than. Oh, that's way better. Yeah. Okay, fill randoms with numbers. Okay, all good so far?
I think so.
Okay, then we call linear search function 1,000 times. Still looks okay. I'm gonna run
Yeah.
this with size. And okay, we sort it once. That is gonna get painful, but because I think sorting takes a long time.
Definitely.
Oops.
Okay. Yeah,
Almost ready.
yeah, almost.
This actually went really fast. We still have like an hour. Okay.
Great.
All right, can you
Hey.
guys help me proof it? Or should we just run it?
We have
Just
the
run it.
seed. The seed is initialized before we call the randoms. We initialize. I mean, I think it should work fine,
Okay.
but
Okay.
well, obviously now it's gonna get really big.
It's weird. It's not like increasing. Do we have to run it?
Might have to do it
Oh,
more
zero.
times or something.
Okay, what do you think? Which number?
Well, the problem here is that it's like taking forever. So we're going all the way to 25 million. I mean, you can see that it's increasing, right?
Oh, it's
Linear,
increasing for linear.
linear is increasing pretty well.
It is, and binary search is staying the same. Oh, that's great.
Well, no, it's just because it's so small that we can't tell, I guess.
Well, yeah.
I wonder why it's taking so long if it's like reporting such short times. Or no, it's because we're doing it 1,000 times. Oops.
Should we do it less?
No, it's fine. We want precision, and so doing it lots of times is probably a good idea.
Okay, sounds good.
So yeah, the only downside is that obviously it's going to take a long time.
We will.
So yeah, I mean, looks good. If we wanted to let it run for a really long time, then with a bigger like end,
Yeah.
then we could probably get like a really nice set of data because he wants to do the Google Sheet thing, right?
Sounds good. We can tweak the stuff slightly.
Constants, yeah. Num
Num
times.
I am gonna go with less precision.
Yeah, 10,000 is a bit much probably, but 1,000 is probably good.
Max Rand looks okay.
Yeah. Or wait.
Can we also time how long it takes to sort? Because I'm just curious. Is that okay?
Sure.
Yeah, we can.
No, it'll probably be negligible, right? It's not gonna be 1 second, right? I don't know.
Because, yeah, I guess. Yeah, we won't be able to measure it most likely.
All right, I'll just pop it in, but yeah, I really doubt I'm gonna get it. trying to sort for the
Just start minus n.
All right, are we ready?
I think this should, yeah, I guess we're ready.
Okay.
Yeah, I thought so. It's just gonna be 0 for like forever. Not like it matters all that much.
Okay. Anyone want to start the Google sheet while this is going?
I mean,
Oh, time to sort is taking time. Oh, yay.
oh
I was
gosh.
still not understanding why it was 0. So
Oh, why which is 0?
like
All of them?
everything.
Oh,
Yeah. Like
Yeah.
why is it 0?
It's
It's
just so
just-
fast that it's
so
close
Just
to zero.
because?
It's because
Okay.
we're using the time clock, which like measures seconds, and computers run really fast.
Okay, yeah, no, and then all of a sudden there's a 2 and an 8.
Yeah, that's really interesting. Looks like sorting a ginormous vector takes the sort algorithm a long time.
Sorting is very slow.
Okay. No. I was just like maybe I'm not understanding something or
I
okay.
don't I think you understand.
I mean, yeah.
Well, I'm gonna have to go back and like digest everything because you guys are way faster than me. But this is pretty cool actually.
Okay, maybe we want more data points if we're only gonna get that many useful ones. Maybe we should start higher than 10.
Higher than, oh, here?
Yeah. Maybe we could start, where does it start actually getting interesting? Like, wait, can you scroll up in the, like,
Oh,
results?
sure. It starts getting interesting here at 31.
Okay, so like 31,000. Okay, then maybe we could start at like 10,000 or something.
Okay, and we can
Just
get
because.
more data points. I mean, it's multiplying by 4 isn't
Yeah,
even.
that'd be a good idea. Nice.
That's it. And so,
Then we might want to make the max vector size bigger than, dang.
yeah. Why is it still? Let's just keep fiddling with it.
Oh, because yeah, you need more than 40 million because it's gonna multiply by 4, so it would be 40 million and then 24
Oh,
times 4.
I see.
What is that? 696. Yeah.
Okay, it's really uninteresting. Maybe we should get Anand over here.
Yeah, maybe.
Yeah. Maybe if we, I don't know. Five. So I just made the value defined for binary search really bad because the lower or higher it is, the more it'll have to go through and do it. But I don't know. Or we could find a better way to measure it.
I remember finding something called clock when I was trying to look for how to measure the first time that we did it.
Clock?
Yeah, let me look that up again. Clock.
Okay.
Okay.
We have time and we probably get better data.
Okay. Um, okay, that's really interesting. Yeah, it looks pretty similar to what we're doing actually.
Oh, really?
Yeah, so maybe we do need time.h now, but
Okay.
yeah. So basically what we want to do is make a clock underscore t, right?
Up here somewhere?
Yeah, like a clock underscore t, right? And then just name it something. I would probably not name it clock.
No, our clock or something.
They named it t, which could work for pretty well.
Yeah.
And then what you want to do is right before you want to store, right when you want to start the timer, right? You
Yeah.
say t equals clock and then parentheses.
Beautiful. Look at that.
And then what you want to do at the end is say that t is equal to clock minus t. Equals clock minus t. Yeah, that works.
Oh, and what will it give us?
I don't know exactly, but it says it'll be the number of clock ticks related to a particular program execution. So it's like units of time constant, but system specific. So maybe not the best idea on a cloud, I guess, but.
So this is, sorry.
I don't know if it's actually better. I just know that there's a different way to do it, and it looks like it might be better.
Okay. Double, sure. Let's try it. And let's print it. It's way better. Oh my goodness, that's amazing.
So yeah, that's not precisely in like seconds or anything, but it is better.
But
It
we
looks
can
like.
graph it. Right? We can graph
Yeah.
it. That's perfect. Okay, what do you think of that?
I mean, it looks nice.
Beautiful. I love this. This is so much better. No, because that will dirty up our stuff. Sport. Clock minus, what was it?
T.
T? Okay. Yeah, the reason I didn't do it in the C out is because it could dirty up the.
Yeah, I figured.
Clock. And then we can do
Semicolon.
oh, thanks. And then we can do.
Oh shoot, you missed it on the last clock too.
Ooh, thanks. Okay, and then we can do this.
Yeah, and remember to replace NTS. Yeah.
Right. Sound good? Did we get it all?
I
And we can
think
delete
so.
Oops, time test. Oh, we're doing this now. Sort takes
Oh,
forever.
dang.
Dang, binary search hard.
Okay,
Wow.
now we can definitely graph this. Okay, who wants to
Yay.
do the sheets?
I can do it. I like sheets.
Okay, go for it.
I'll
but
make it a
you're gonna
shared Google Sheet if you want, but I don't know how to make it. I could make it private, but then like it would be really
have- do
hard to
you
share.
do you
Shoot.
want me to like copy paste this, or do you just want to like write it?
It might be easier to write it than try to format all that.
Agreed. All right, so we'll just chill and like while you
Okay.
do this.
So wait, should I make? I'm trying to decide like where I should put what kind of like sheet I should make because I don't know how to use like private sheets or whatever.
I don't know either.
Should I just do it in like a Google Sheet and then share it or something?
Sure, that's what. Yeah, Google
Yeah,
is.
Anon doesn't really like when like we make stuff that requires like accounts or stuff, but whatever.
Yeah, but it's fine. We all trust each other. And we can take screenshots.
Not gonna steal my information.
Right. No.
Okay. Okay, so let's see. What should I name it? Let's call it C++ linear vs binary.
This is so
search.
much better than the second.
Now I just have to start typing, huh? Okay, so I'm gonna.
Hey guys, is everything okay? All going strong?
Yeah, I think so.
You guys are having a good time?
Okay, so
Always keep in mind that you got to keep everybody with you, all right? Because when you're in the heat of coding, right? Some of you may not have experienced it as many times, but when you're in the heat of coding, you just forget. You know, some people just will drop off. You just need to keep looking back and make sure that everybody understands what's going on. Oh, you're actually printing out these times.
Oh, so we did something different. We kept getting 0 for binary search. So Hiram found this.
I'm sorry. Yeah, let me follow. So this is for the binary search. You're trying to time it, right?
Yeah.
Okay.
We kept getting 0s, so we switched to clock.
I don't understand. You kept it at 0? What do you mean kept it at 0?
No, we kept getting 0 for our time for binary search.
Oh, because by the way, time takes a long argument. I don't. Are you calling time with no parameter?
Well, no, we're using clock now.
Oh, I see. Then if you all right. All right. Using clock is a bit more. I prefer if we didn't use clock. The reason I say that is because clock allows you finer grain control. Yes, because you can, right? It gives you a very fine clock, but it requires you to know certain things that really don't help us in CS2A. And then given that we only have a certain number of classes left, I don't want even 20% of the class to of time left to be. Just use time, and that's why we did that Alexander's trick last time, right? We did the 1000. You're actually already doing that anyway. If you're using clock, you don't need to do that anymore, right? Because clock gives you very fine grained control. You can go up to nanoseconds, my milliseconds anyway, right? Microseconds. So if you're using the clock variable, the clock object, you don't need to repeat and take the average. But what we do here using Alexander's technique is basically just to get the same effect without having to use all that sophistication. Yeah, does that make sense? That's the reason we're using time.
Could you help us, because we keep getting 0 when we did time?
On time, you're getting 0 return value time?
Only for binary search. It's too fast.
No, I don't think so. That shouldn't be the case. So start TS. Is that what you're talking about? Oh,
no,
here.
we kept getting, yeah, we kept getting 0. So,
Yeah, don't use clock. You know, yeah, because using clock requires a whole lot of things. You need to know about some defined constants and divide the result by something else. And I need to look up the, yeah, the fact that you could be programming for a while, but you still need to look up the documentation for something is usually a sign that you should try and use easier methods if possible. Because there's a very good chance that, you know, 3 years from now, you're still going to have to look up documentation to know what that is. Yes? Because these things, you don't tend to use that many.
yeah.
Yeah, just use time. That should work, right?
Yeah, one second. I have to do binary search.
Oh, I see. Yeah. Oh, and you still have the t equals clock. No, on line 87.
Yeah.
Oh, I see. You're gonna. Okay, here you go. All right. Okay. Good. All right. So NTS. Oh, wait. Yeah, line 87. Oh, 71.
So we keep getting 0. Like,
Let's take a look at that. What are you getting 0 for? Oh, I see. Time.
binary.
All right, let's take a look. What is that line? Time per linear search with. Okay, you're probably integer division. Oh, you're not doing that. Okay, good. Let's take a look. Time per linear search. Okay, that's the one. Time per linear search. NTS minus dot TS. Okay, NTS is time 0. Dot TS. And what is your num times variable?
1,000.
Okay. All right. Still, it's a linear search. 1,000. And what's the size of the vector? Oh, 243K. That's the size. Oh my gosh, 2.4 million items in your vector.
21 million.
No. You say time per linear search with size 243 followed by 4 zeros. In the output. The first line of output.
Yeah, I'm trying to figure out why it's so big.
Let's take a look. Hang on. Why? Right. Where is that line in the code? Let's take a really quick look. Is that okay with you guys if I look at the code now?
Yeah.
Yeah. Yes or no?
Yeah.
Do you want to look at this yourself, or do you want me to look at it?
No, can you help?
You can look at it.
Okay. All right. Good. Let me take a look at it. All right. So all right, and then that's a linear search. Okay. Start. We take the start time. All right. You call the method a certain number of times. Okay. Oh, you're looking for the same value each time.
Yeah.
Okay. All right. So we'll fix that. You should look for a different value, but you should look for the exact same value in both cases. But because the same value, maybe it was the very first item.
So
In your linear search.
oh, it probably is for linear search.
Yeah, so it's going to return 0 every single time, and the average is going to be 0. So we should look for different items each time. No, don't do that. Don't do that. Value to find should not be. No. Get rid of that line.
So,
to find should be dynamic and every single time.
This is guaranteed almost to be the worst case for binary search. So I figured it's good to show off like the worst case.
Oh, I see. You want to force it into a case where it's.
Yeah, I'm trying to get it to like give us anything.
It's not going to be the worst case, by the way, because it's one of the extremes, isn't it? Oh yeah, because it'll keep on chopping and it'll go.
It's almost worst case.
Okay. Yeah, logarithmic times. You want to do that? Yeah. Okay. You need to resort to tricks like that if you're just doing one value and say, okay, what's the worst case, right? But to do something like empirical performance, we should basically say we'll just select a random value at runtime. We're going to run 1,000 random values. We're going to find 1,000 random values. Some of them may not be found. That is really the worst case.
Should we still seed it?
Right? If you don't find something, that is the worst case. Oh, you should never call srand within. Yeah. All right. Oh, I see. You have a seed.
Yeah, we were trying to make it.
Is that okay? Can we fix up a few things in here?
Yeah.
Okay, good. All right. So good. Let's go in order. Get rid of the first line 48. We don't want line 48. Get rid of line 48. Okay, good. Now, there you go. Now set up on line 54, hit enter. Line 54, hit enter. Right? Start experiment and put a comment saying start experiment 1 with linear search, right? Start experiment 1 with the linear search. we'll print out 2 columns of numbers. Okay, we'll print out a column of numbers for linear search, another column for binary search. Previously, I was thinking we'll print 1 column, vector size, linear, binary. So that is going to be more of a problem. So, but you can do that for homework if you want. Okay, all right. Now on the next line, set the seed to a control seed that we can remember. Great, great. Okay. In fact, take that line and put it before the experiment 1 comment, right? Even including the comment, Yeah. Once we get the control seed, we are going to do two experiments with the same control seed. Okay. All right. Now we're going to this srand with that seed. Srand with that seed. Okay, now we've gotten to a predictable place in RAND. Yes? Okay, from now on, we control all the randoms that are going to come out. Okay, now you start your for loop. And inside the for loop, you're going to, oh, I see, you can put it right there. Yeah, okay. Oh, you're doing a fresh new code. Okay, good. That's fine. Okay, inside the for loop, you're going to max spec size n. You can basically say n times equals 10 itself, right? Because it'll be easier for us to debug right now. The last one, a max spec size, and then n times equals 10 on the very end. And n times equals 5, maybe it'll grow faster.
Oh, at the end.
At the very end, sorry.
Got it.
Okay, all right. Now you've set the seed. Have you got the vector initialized? Have you got the vector initialized already? The vector of randoms?
No, it's
Oh, yeah,
ready.
put it right up front. Make that go all the way before even you get the seed, set the control seed. After you do the variable declaration, you're going to fill up the vector, right? So copy that, copy the line 70 all the way. Yeah, okay, great. Yeah, copy that and put it right at the top after your unsigned long start TS and so on. Now you can put it there too if you want. Okay, all right, good. Did you do that? Where's it gone? Oh, you want to put it there? Okay.
Oh, yeah.
All right. Okay. Now you're going to fill up the vector. Good. Rand. Oh, I see. Hang on, just one sec. Rand. Oh, I see. For each of those items, random that size, I plus. Okay. Max rand is the thing. You're big. Oh, you're getting a big rand and then percent modulo by max rand. Okay. All right. Good. Now, here, what you want to do is the first line should be comment. The comment in the first line should be find the value to create a value to find. Create a value to find. Okay, and then you're going to copy that line where you say big rand percent max rand. That's the value you're going to find. So you're going to say, yeah, there. You can copy that and put it there. All right. Now, value to find equals that. Hey, Agnes, are you here? Agnes gone? Okay, so she's going to watch the video. Is it time already? No, we got a half hour. Okay. All right.
What's the type?
No. We shouldn't start time now. This is all priming the vector, right? Because priming the vector shouldn't be part of our timing. Priming the vector, everything should be, the only thing we should time is a search.
Great. I'm making the value defined.
Oh, yeah, value to find. Say value _to find. Value _to.
What's the type?
Oh, I see. What is the type of the vector? Randoms of I.
Oh, good question.
Unsigned long. I think it's unsigned long.
Yeah.
Value, or just say val. Just say val equals. No, it should be lowercase, right? It's not a const. Yeah. All right. Now, oh, I see. We're doing that big rand, and it's a calculation, but it's going to be the same. So we can insert. We can try and refine this later, but this is thinning it down. This is an important thinning down part. Okay, so let's go back. Yeah, all right, good. All right, good. Big rand, you're getting a random number, and put a comment there saying, for the moment, ignore the overhead introduced by big rand. Okay, put a comment there. For the moment, we'll ignore the overhead introduced by big rand in our timing. Is everybody? Does everybody understand why we're making that comment there? Yeah, because we're timing. Yeah. Oh no, wait. One sec. Oh, srand, okay, srand seed. Oh, we aren't timing. That's what you're saying. Okay, we need to time. So yeah, take the start TS before the for loop, and then we need to take one more start. Time. Yeah, after that. Thanks. Okay, now do the find. In the for loop, you have to do the find after the Yeah.
Are we still doing num?
No loop there, because you have a loop already. So you just need to, that line only, put it there. Okay. And then this is your value to find, val, just val, not value underscore to find, just val. Okay. All right. Now that loop is going to generate a random value and find it in the vector. Yes or no?
Yes.
Okay. All right. Now, when it's done that, how many times are we doing that, Max? Oh, wait a sec.
Yeah.
That should be a number of times, not, n equals 0. Oh, yeah. I forgot all these loops. That need to be changed. N less than or equal to then, right? N plus plus, N plus plus, and then you can make it, because you start at 1, you should go to less than or equal to, or start at 0 and go to less than. That's a more common pattern. All right, and there you go. So then you can divide by the num times to get the time for linear. Okay, now you can do exactly the same thing for V2. Get rid of the blank line even between. And in fact, you can condense that even more by putting the big rand % max rand instead of val right there. You don't need that intermediate variable even. Yeah. Okay. All right. And then you can repeat the whole block for this. In fact, you know what? What you need to, are you printing n? Oh, so you are.
Oh, yeah.
You are putting n and time per linear space. That's good. That's good. Just combine all that. Remove the blank lines. Make that a chunk, so you can take that chunk and copy it one more time and change the V1 to V2 when you got the other one. Also, when it comes to the output, you'll find it easier not to print all the text, because you're going to be copying and pasting into a Google spreadsheet. Just print the numbers, n, comma, and the other one you can copy and paste, and Google will take care of the parsing for you. N and then comma and then time per search. But you need a header there saying, oh no, you can, the first bunch of numbers is going to come from linear search. Okay. Oh no, but you need n. You're not printing n. C out, left shift n, and then
why would we print out n?
Because you're going to graph it, right? You're going to say for this size n, for n, n equals 10, you're going to have this many seconds. For n equals 100, you're going to have that many seconds, and so on, right?
But randoms is always the same size right now.
I thought we were running a loop where we had.
No, we did that down here, but.
Yeah. I'm so sorry. Just copy that. Just copy that loop, and we'll do the indentation again. Just copy that for. That one. Just put it on top. Thank you, Hiram. You're actually thinking 2 steps ahead. Not all the way there. No, after you filled up the vector, just before start the experiment, right? Start the experiment. There you go. Don't put it there. Don't put it there. After start the experiment, that's where it needs to go. Right? Hang on.
And then we have to.
And I think the S-rand, does the S-rand need to go before? Yeah, the S-rand needs to go before. The S-rand needs to go before. The S-rand needs to go immediately after start the experiment, because start the experiment. Okay, great. All right, and that whole chunk from start the experiment to that is that block for V2. I think that is good, right? So now you got not max.
Max vec size isn't used yet.
Oh, you're using two different n's here now, is it? No, that's good. Oh, n times equals 5. N times equals 5.
We're not using n
yet. We will use that very soon. We're going to see out the n.
But n isn't in use yet.
But n isn't in use yet.
Yeah, we're not using n yet. Like, it does nothing.
Now the cout, but we're going to modify the cout statement on line 78 to print.
Yeah,
yes.
But right.
Oh, we're not even using it. Oh, we're not declaring the vector here. So yeah, you need to declare the vector. I'm afraid before the. No, not. Oh, I see the vector that we need to search. We're going to modify the timing just slightly. Okay, we're not going to. Here's what we're going to do. Yeah. Put the vector in there. The timing. Where is this start TS? Okay. What we need to do is Yeah, the vector should be getting filled outside, and then we do this NTS, and then no, not there. No, what we need to do. You are printing the time there. Okay, all right. So you're filling the vector. You're filling the vector time and the average. Okay. I think. Thank you, Alexandria. That should do it, right? I think put a comma. I think Google cannot parse the space.
Okay,
Or a tab. I think a tab would do, but tab or comma. I think.
1 second.
Is that okay? I just want to eyeball it one more time just to make sure. It looks okay. Alexander, did you take a look at it also, or one of you other guys? So, oops. All right. So, you're starting at 10,000. You're not starting at 0.
Okay.
No, start at 100. Start at 100. I think 100 would be good. So 100, and then up to what? And what's max flex size?
50.
I think that's too big. That's 50 million, right? I think 1 million should do now. You'll have a lot of values within 1 million, yes, because you're going in multiples of 5. Just say 1 million, yeah, because then we'll have a good chance of getting a result before end of class. Okay, you declared the all right, and that's good. All right, and then stuffing it, and then you are timing it right there. Where's the end? And then calculating. One sec. Okay, all right. So here's what we need to do. Oh, you're filling the vector that many times, and then you're gonna. Oh, you got all of that. All right, you see out, and I think that I think that looks okay to me. Can you copy the whole thing and for V2 also? You should be able to run it and plot it now too. No, not S9. I'm sorry. Hiram is doing all the right things, and I'm correcting him, saying, "Hey, don't do the right things." Okay, so which is kind of cool. All right, good. Yeah, did you copy it? Did you copy it and make the V2 also? And this should be V2 with the linear, yeah, binary. No, start experiment 2 with binary search. Set the same seed. Okay, that's good. And V2, and then yeah. And all right, maybe we need to put a tag before so that when we copy and paste, it'll be easier. You can put a cout starting binary search experiment, and then up there you can say starting linear search experiment, right? So when you copy and paste, you know which bits to. Yeah. I don't know. This is fun for me anyway. I'm having a great deal of fun. You know, you guys watching you guys do this. I don't know if this is fun for you. Is this fun for you? Fun for you guys? I hope so. All right. Okay. Cool.
Yeah.
All right. So run. I think it should run now, right? It should run. Why is it taking this long? It should have come out already, with at least the first one. Do you have a cout and no, something is wacky here. Wait a sec. And it's doing linear search. 1,000 times. Just can we turn that into 100? Maybe that's too. And why? Actually, hang on. What is it? Let me find out what it's 100. The size of the vector is 100, and number of times is what is your number of times?
1,000.
Yeah, yeah. So 100,000. That shouldn't take a long time. That shouldn't really take a long time. Inside for loop on line 71, can you just do a random cout saying cout I'm the innermost loop? Just do a cout and then run it. Yeah, and is it even getting there? Oh, it is there. It is okay. Right. I also print the value of I for all the points and print the value of I.
Oh, I found it. Oops, typo.
What is it?
It was n++ right there, not I++.
Where is n++?
Oh, and I must have done it.
No. It's binary, not binary, linear. She's talking about linear.
Yeah, I messed up in both of them. I fixed it.
I don't understand. Where is it gone?
Here, I have this. I had at line 71.
No, that's dangerous, right? So you can do I
Yeah,
0.
That's what I fixed.
Oh, you fixed that too. You changed that to n plus plus?
No, I changed it back. It was.
Oh, it was n plus plus before.
Yeah.
How could you change it while Hiram is editing it?
Oh, I'm editing. Sorry.
Oh, you're editing it?
Yeah.
I see. Okay, I thought it was Hiram. Okay, all right. Thank you, Alex.
No, we have the same voice.
Okay. All right. Why is it? All right. So you need to get to a decent sized vector before it even starts spitting out these times, right? So that's good. So now we can increase the size of the vector. I think. Let's go, Max. Yeah, I did change number of times. A number of times is not the issue. Yeah, vector size. Let's make that 10 million. 10 million. Run it again. Oh, you can even go to 50 million like you guys had before. Maybe that's what you did, right? Maybe we can go to 100 million, I think even, right? Maybe that's what you guys, did you guys experiment and find out that number?
Yeah, we were having trouble. We kept getting zero.
If you told me that, I would have said, yes, that's fine. I thought you were just playing around.
No.
Okay, all right, but it looks good. Now, I think the next one should be 0.006, right? Not close to it anyway. Because it's linear. We can tell that the difference between, no, I see we're going times 5. So the previous, you can go even bigger now. I think you can go bigger, or you can play around with the parameters, right? You can say I want to do more times and divide, get a higher precision value result. You can do all those things. By the way, you guys are absolutely confident of methods work, right? They do return the right values. Yes.
I think so.
Okay. All right. Good. That's just fine. I'll take your word for it. So is it so the point? Well, I don't know. You got the hang of it anyway. So you just need to generate enough data points to create a curve and a line. I think a curve and a line, but you should play around with it and find out. Now you got these numbers. Why is it? You can make it. You can slow it down a little bit. You can actually use random strings instead of random integers. That'll slow down the search considerably. Right? So if you generate names, random names, for example, like you do in your quest, just pick alternating vowels and consonants and create a vector of strings. Then your binary search, even sort will work. Sort will also work because you're using standard sort. So everything should work, even string comparisons, everything should work. So if you use a string array, string vector instead of a numeric vector, your times will be a whole lot more, visible. Right now, I think you may even go up to, like 100, 1,000 million, a billion elements too, right? I think 1,000 times 1,000 times 1,000. Yeah. It does look like a line to me, although we can't tell, right? Because the x-axis ticks are multiples of 5, whereas the y-axis increments seem to be linear. So it seems to be sublinear at this point because the x direction is growing by multiples of 5. No, linear, because this is also going by constant factor. That's also going by constant.
Why is it stopping?
Oh, you mean it's stopping soon? Too soon?
Yeah.
Yeah. Why is it stopping too soon? Maybe times 5. Oh, because we're doing times 5, and that times 5 is probably less than max fixed size. What is that number you got out there? 1,953,125,000. So that's 195 million. Yes, that's 195 million, isn't it?
Yeah.
195. That's 200 million times 5 is 1 billion. That's why. But still, you should do the 1 billion. Why is it not doing a 1 billion? Because that's 190. That's 195. 195 million. So it's less than 2 billion. 2 million. That's less than 200 million. So times 5 should take that to a billion. But this should be less than a billion. That means it should print that last thing, which is times 5 of that. Yes.
Yeah,
Why is it not doing that?
I just changed it to test it. Yeah, it's crashing, I think.
It can't crash. Why would it crash?
I don't
we're
know.
not consuming memory. We're not consuming resources here. It's just a loop.
But it's not getting to binary search.
Oh, I see. It's dying before it gets to binary search.
Yeah.
It's possible. Here's what I think is possible, right? And just a theory that online GDB is killing the process, killing all processes that take more than a certain number of seconds. It's possible. You can just create a random online GDB program that does sleep 60 seconds, right? And then see if it just gets killed by online GDB in 5 seconds. You can copy the whole thing into cpp.sh. Just copy the whole thing, Command A, Control A and Command, Control A copy. Go to cpp.sh. Yeah, paste it here and run it. We'll see if we get the same behavior. Is that it? No, Command A and paste, Control A and paste. You got the whole thing, right? Control A, paste. Okay, good. This should, let's see if we get the same behavior here. Yeah, how did you get that? How was the old, I thought you did a Control A and then a paste.
Maybe I messed up.
This is also crashing?
Not.
Oh, it said exit code 0, and it
Yeah.
even before. Oh, I think I know why. It is because a resource. I thought we were not using resources, but we are actually using resources, and the resource we're using is actually memory because we're allocating a big vector. Yes. In there, you're allocating a vector of size n. Yes.
Yeah.
Yes or no? Inside the loop, you're asking for so much memory. I don't know. Nobody's answering me.
Oh, yeah, it's right here.
Okay, so that's why online GDB says no. It can kill you. Maybe it starts you within a Docker image, where everything is limited, right? And then if you ask for more than that, it's just going to die.
I see. I'm trying to recreate it in my shell.
No, we can get around this by not asking for such a big vector, but instead, what we can do is just do more iterations, right? Instead of asking for a billion items, right, in the vector, we could say our vector size is going to be limited by, I don't know, 10 million, right? Let's not go beyond 10 million, but the number of times we're going to run the loop, let's say that's going to be 100,000, right? Let's run the loop 100,000 times and divide by 100,000 num times. Change the num times to 100,000. I bet even online GDB will let you do it. Go back to online GDB. I think we can fix it. Okay, because we just want to make sure we are economical in resource requests. Okay, number of times 100,000. Yeah, I think this should work. This will work. Okay. There you go. And we even get finer grained numbers now, right? Because we're running so many times, it's actually getting these values sooner too. Yes. Now, if you play around with these numbers, you can reduce 100,000 to maybe 10,000, right? And you'll see that it works all the way through. It'll even go to binary search now because we're not asking for that big vector. That's why we got killed before. Does that make sense? One of the yeah, but I think it's not a problem just with using online resources, online GDB and things like that. The same problem could have bit us even if we were doing it on our own PC, right? Because we don't know how much memory we have, for example, and then we just ask for a big array and we don't even think about it because it's a local array. There, I think you get much better points now too, because we're taking a much bigger sum, 100,000 samples and dividing by 100,000. Previously, we were only dividing 1,000 by 1,000. Yes, 1,000 samples by 1,000. Now we're taking 100,000 samples and dividing by 100,000. That's why we're getting more fine-grained results. So you can change that to 10,000. I think it'll be a good compromise between getting results as well as letting an online GDB run it. So we change it to a 10,000, num times to a 10,000, and you can leave the size of the array the same, right? This should run all the way through, but at the same time, I think, right? It should run all the way through, but at the same time, it will give us reasonable numbers to plot. You see, even for a vector of size 12,500, we're actually getting a number now. We didn't get a number before, right? Because we only had 1,000 samples to sum. We didn't get that number. Now we have 10,000 samples to sum. That's why we're getting these numbers. Now this is easily plottable, right? You can just copy this into a Google Sheet or Excel spreadsheet. In fact, even if you just do a paste in there, I think the comma will be interpreted correctly.
Oh, I think we forgot to sort in
Oh,
binary.
we forgot to sort. Yeah. Okay, you got to sort. But sort it outside the timing loop, right? Yeah, sort it. Oh, I see. So the way to do this. I think, but each time is a different vector. That's fine. It's a different vector each time, yes? Oh, you want to sort it after? No, not there. You want to sort it after the filling, right? If you sort it before the filling and then you fill it with randoms, your sorting is lost. Yes? You got to sort it not when the vector is empty. You got to sort it after it's full. Well, you can play around with the numbers now anyway, guys, because now you know that maybe 10,000, even 10,000 is too big, right? Maybe you can go with, or you can run it for a longer time. I think if you just run it on a PC or some computer, come back after a half hour, you can just see all the numbers out there. You can copy and paste that, and you should be able to share that too. This is actually looking nice, right? You got 1, 3, 13. And if you look at it, it is actually, I think, going in multiples of 5, right? 3 times 5. What is 3 times 5? 15, right? Yeah, so the left-hand side is going by times 5, yes? The size of the vector is times 5, and the time taken is also roughly times 5, yes?
Mhm.
So they're both going linearly, and that is the trend we want to see in the graph. But we can't see that in the numbers, but you'll see it in the picture, right? So you'll see in the picture. But that's basically it, guys. I think you've finished it. It's a very nice little project. We started it in class. You just wrapped it all up, and it's going. You're getting real useful numbers to generate a nice intuition. So very nice post to make, right? And say, well, this is what we found in our experiments, and it's really cool. I think it's really cool. Okay, so because it gives you a real feel, right? Now you know. Later on, when you speed up an algorithm, a real world algorithm, right? Someone's paying you to do that. You'll know in your mind. You'll know. Well, you know, when I speed up, this is the kind of thing that's happening, and this is the kind of win I can experience. It's going to take a while, right? We shouldn't be sticking around, but you guys can, you know, play around. I guess if you want, you can play around with other code if you want while this is running in the background. You can just leave it running in a tab, right? It's somewhere in the cloud, their machine, right? Their image anyway, right? Their what do you call that? Container. Their container. All right. So if you have any other questions, happy to talk about that. Don't kill this tab, okay? Just leave it running so that I am pretty sure in 1 hour you'll get the results, right? You leave it running for 1 hour, you'll get all the numbers in 1 hour. I think. How big is this? 100, 1 million? Is it up to 1 million now? The vector size 1 million, right?
Yeah.
10?
Oh,
The last one I printed was 1.5 million.
yeah.
And you're going up to 10. So the next one is going to be 7.5 million. Okay. So why is it taking this long? Oh, because we're running it so many times. That's why. Okay. We're running it so many times and taking the average, and that's why each one is taking this long. I thought maybe it's some overhead we can cut. Maybe we're doing the counting or sorting redundantly and it should be moved outside the loop. No, it's not. This is all necessary. All this time is necessary. In fact, the reason we're getting these fine-grained 0.00041 and all those things, right? Very fine-grained counts is because we're willing to be patient and let it run for a long time, right? If we're not patient and say, no, I can't wait this long. I need it to run only 10 times and take the average over 10, we're just going to get a lot of zeros. So if we're patient, we get, you know, better results. So you can leave this running, Alexandria, but don't kill the tab. Come back in an hour or so, get the numbers, and you can share with the rest of us in the forums or, you know, something like that. I'm pretty sure it'll. I hope. Yeah, that's the danger of online GDB, right? If it's like this, no input and no output, right? Like this. Who knows how online GDB is doing it, right? I don't know if it's actually actively polling the kernel to see if this process is actually doing something or is it stuck, right? If it thinks that this is stuck, like in JavaScript, it's not seeing any back and forth, and it sends it a kill signal and something, and your program dies. That's the danger that you got to saying that you can't run it in online GDB. Then you got to run it on your own machine.
I can use my own machine.
No, this is, you're running it on online GDB inside on
Yeah,
your.
it is.
Yeah, run it on your own machine or on Hiram's Linux PC, right? I think on Hiram's Linux PC. There you go. Binary is already started. PC is the binary so fast already, right? So you can see that it's so quick. But now you know that with 10,000 num times 10,000, it's only taking like 10 minutes, right? So now you can try bigger arrays. So you can get counts even for the binary. Because the way to get counts for the binary is to just run it even more times. Because each count is going to be so tiny, you got to add up lots of them to get something on the numerator. So the only way you can get non-zero counts for binary is to run it even more times than 10,000, right? Even more times than 10,000 you can get. In fact, you know what? Let's for binary. Let's change it. Just leave everything the same. Just go to the binary part, where num times, right? Where num times, you say where I less than 10 times num times, 10 times num times, right? Instead of 10 times, and then where you divide, that should also be 10 times num times, and the whole thing should be within parentheses. 10. Or you can get rid of the double and say 10.0 times num times. That's automatically also. All right. So I think that might actually give us numbers. Okay. But now we are forced to read through the linear. That's like 10 minutes. But I think that's one of the tricks, right? So that's one of the ways we can find out how we can get numbers from both sides. A binary, that'll work, because now we're running each one 100,000 times. So what used to be 0 before, I don't know, maybe it'll be like 10 or 15. 15 divided by 100,000 is going to be 1.5 times 10 to the minus 5, right? Or 10 to the minus 4. And I think that'll print, right? So it'll be 1.5 times 10 to the minus 4 because it's divided by 100,000. Things like that. Yeah. Are you guys okay with this so far? Was this a useful class? Yeah, I don't think we covered any really, and I don't think we're supposed to cover new ground today, being a holiday and it's not a mandatory class and people are not expected to. All right, so I don't think we covered any new ground. Did we cover any new ground today? We're just playing around with existing code. If we did cover new ground, please make sure to tell your classmates, okay, whoever you're in contact with, tell your classmates, right? Something statics. Tell them we did statics, but it was supposed to be by yourselves anyway. So yeah, tell your classmates we covered statics. All right, is that good? Anything else? What time is it now, by the way? No, it's 10 o'clock. It's past class time, and you guys are still around, even though it's Veterans Day. So yeah, thank you so much for that. But I had a great time. Just watching you guys code like this, and it was fun. And it's a useful exercise, right? You basically take this and bring it to bear on anything you do. Later on, you come up with a brand new algorithm of your own, adapt it to a particular. You can test things like this. And eventually, even when you go in front of a board and say, we're going to change your product and switch this algorithm for that, and these are the results we've done, right? And these are the kinds of things you would expect from your engineers too, right? And, it'll be fun. So next class, I think, what is it? This is week 9. This is the end of week 9. We got 10, and then we only got half of week 11. No. This is what is this? How many weeks do we have left? Right? We have 2 weeks in November and 1 week in December. Is that it? No, we got 3 weeks in November. We got 3 weeks in November. So we got 4 weeks left. I'm confident we can cover all the material. That I'm not worried about. All right, let's see. So this is this week. Okay, that's next week starts on 15, 22, 29. Okay, so we got 4 weeks left. We got 4 weeks left, and we got plenty of time We'll play with other stuff too. And we'll start working. That's funny. For binary search, it gave you a number for 12,500, but no number for 62,500. Those are mysteries you've got to uncover, right? Why? That's an anomaly, isn't it? So why is that non-zero and everything else zero? Something else, something funky is going on there. So I can see that there's a bug. Okay, there's some kind of a bug there. You guys have to. So I'll be interested to know what that bug was, right? If someone can follow up on that and say, why did this happen? Why did this happen? So I need to find out why something is right. If you can find out and post, I would be very, very interested to know why that happened, right? Obviously, we can find out if we all spend time together and look at it, but it's past time, and I appreciate some of you want to go. And plus, it's really a juicy morsel. Something wrong like that. Something goes wrong like that, that it's got to have an easy fix, hopefully, right? Most of the time, got to have an easy fix, but it's wrong anyway. Those are the tasty things that you find by the sidewalk, right? As you're debugging your code, because the easy wins, right? Low-hanging fruit. So that's something you can look forward to. You can fix that and then post in the forums too. We ran this experiment and we found this anomalous behavior, and investigating further, this is the reason for the anomalous behavior. Is that okay? I look forward to that post if one of you can make that. But are you with me that behavior is anomalous? Yes.
Maybe it could be random.
No, but yeah, okay. It could be random, but there are very slim probability it's random, because as you see already, you're averaging over a whole lot of whole number of trials. Yes. So if you run it again and see the same behavior again, then there's something wacky there. If you keep seeing the behavior again and again, then okay, well, we need to find out why that's going on. Right? So it's possible, as Alexandria said, that, okay, there's a one-off occurrence, right? So run again, and then see if the same thing happens, right? For 12,500, one experiment. So, and then we try and find out what's the reason for that? Perhaps the reason is when the vector crossed a certain threshold, online GDB said, okay, well, this kind of Docker image is going in a swap for running this program, because all of these programs are running inside of the containers, right? So online GDB could have a monitor that says, okay, this program is asking for too many resources and this container is not cutting it. So I'm going to move this program to a bigger container. So, or maybe swap, right? Swap is kicking in at that point. Who knows, right? So first time something happens, like in Java, right? If you see a sudden number increase like that, okay, that's when the Java garbage collector kicked in, right? Because everything else is normal and that one too. So like that, maybe that's when the swap happened, right? So those are hypotheses you can come up with, and you can verify these. You can verify these hypotheses, right? Easily by just narrowing it down and creating a case where that should happen and seeing. And even though this machine is located halfway across the world, and it's even a virtual machine, it's not even a real machine, it's a container running in the cloud, but we can still experiment and find out real things about that container, right? By doing this kind of thing. And that's one of the exciting things you can do, right? Anytime you have an open service like online GDB or Google or even questing open to the whole world, people are going to try and find out. Right, so they're going to hit it in all manners of ways. You try and find out, and if it's not working according to how they want it to work, they're going to try and bend it somehow, right? Not even out of malice, right? There's always malicious people out there trying to hack into your system and crack it and crash it and so on. But even the non-malicious folks, there are a lot of people I know who just want to bend the system to do what they want to do, right? So they know, well, Google's got all these services out there, but I still need to do something that Google doesn't offer off the shelf. Right. So I know someone. So I know he started a company after that, which got acquired by Samsung, but he started another company before then, which basically was a company that combined multiple Google services into a single one. So you could basically say, well, you can apply it to anything now, Google, Amazon, Microsoft, and so on. You can say, I want to get this thing done, and it's very routine and robotic. Okay, but it requires a combination of multiple services that Google is offering, right? But that system will just figure out the combination and just create one single macro for you, right? And you can just run it and it'll do all of that. And it didn't go anywhere, but he started a different company. But that's the kind of thing, right? So but they do that. So their system will figure out how to put the various Google services together to deliver some higher order good that you want, which doesn't make sense for Google to offer because you're the only one who's going to want it in the whole world, right? So it would make no sense for Google or Microsoft to say, well, we've got this special thing which will tweet like a, chirp like a, parrot or something like that. So there are people that do these things, like online GDB, I'm sure, like us, right? They're going to say, well, at some point my programs are getting smaller, and I want to find out if it's because of resources used, and they'll create macros that'll basically hit online GDB in different ways and try and figure out. Does this all make sense? Yeah, Tuesday, next Tuesday, week 9, we can start 9, 10, 11, 12. Yeah, 9. We can start talking about stacks already, or we can spend next week also talking about sorting and searching, right? In the context of objects. I don't want to spend too much time on it because you're already doing it for plus 7. But I'm happy to talk more about, sorting, searching, algorithms for it, and so on. Otherwise, what we'll do is next class, we can create a stack, right? We'll create a stack using, actually, you know what? Let's not do stacks next class. We'll do pointers next class, okay? Yeah, we do pointers because the reason I want to do pointers is because if we cover pointers and linked lists before we do stacks, then we can implement stacks using pointers. Because in your quest, I think quest number 8 needs you to require, in quest number 8, you have to implement a stack anyway. But that stack is going to be based on an array, on a vector, not on pointers. So I think it'll be cool if we implement a stack using pointers instead of using the vector. So for that to work, we have to cover pointers before we do stacks. So we'll do pointers. So if you guys are okay, check, and we'll do a comfort check. We'll do a comfort check the next class, how comfortable all of you guys are. See, that's definitely anomalous. It's so you need to figure out why that's going on. And even if it's something to do not with your code, right? Don't spend too much time because your code is quite simple. You may figure out there's nothing wrong with this code. If there's nothing wrong with that code, you can leverage that to figure out what's wrong with online, right? You can figure out the delay happens exactly when the vector goes from this size to that size. So let me create a separate dummy program. Okay, two programs. One of them
run it locally, maybe.
Sorry?
If I run it locally, would it? And it did.
Yeah, you can try running it locally. You can absolutely, and Hiram should run it on his Linux machine too, right? And then those are the ways. That's exactly, thanks, Alexandria, right? So those are the ways in which we, scientifically try and do these things, right? There's someone out there, let's say somewhere in the middle of Kenya, they have a telescope and they spotted a, comet or something, right? And they do some calculations and say, oh, this comet is going to, fly past Earth on, Christmas Eve or something like that. Right? Not everybody is going to just, so all of the observatories around the world, just going to be going, looking at the same location in space, trying to confirm the results. Because, one measurement could always be anomalous. So the way scientists do this is exactly what Alexandria said. It's to basically say, oh, you know what? So we got a sighting from Kenya. Let's try and see if we can verify that from, Los Angeles, right? And maybe, Shanghai. All these places get together. So yeah, Alexandria, you can try that, and Hiram, if you can try that too. Hiram, yeah, can you listen to me, or because you were whistling, right? So yeah, you got to try this too on your Linux PC, right? Try it on your Linux PC. Share the results, both of you, Alexandria, Hiram, maybe make a joint post in Reddit, right, saying, well, anomalous behavior. We try to investigate further. It's actually like a mystery tale, right? Think about it. This is like a mystery tale. This is a mystery tale for software engineers, right? So something is not working. Like what can be the reason, right? It's Clifford Beck. So we gotta go and find out. Hey, why is it not working like we expected it to? Let's try and do the Sherlock Holmes thing, right? Just try and find out what the hell is going on. So that's your mystery to unlock for the rest of today. Hopefully, I will see a post from you guys, right, in the forums. And make it more than just, here's a link to the code we work on. Okay, so do something interesting, like we did this, we ran this. You can also click it and run it, but you'll see something anomalous here. Couldn't see any problems with the the loop itself. So we tried this experiment to see if the problem was only with online GDB, right? I ran it and Hiram ran it, and we got the same numbers, and we looked more. All these interesting discussions. That's the meat of computer science, I think. Are you guys okay with this?
Yeah, sounds good.
All right. Thank you so much for coming by, even though today was a holiday and all. I'm more than happy and available if you guys want, a Zoom session or a class off schedule. Just let me know.
Okay.
And ask Alexandria to catch up on this video and also explain to your other classmates, right, who may have missed out. Thank you very much.
Okay.
Vanny's not here today. Cool. Good. I'll see you guys on Tuesday. You guys coming back on Tuesday?
Okay.
All right, okay. Sometimes I have to ask. All right. Have a great weekend, and I will see you guys in 5 days.
All right, great.
Bye.
Thanks, Professor.